Okay, here's the rest of chapter 26. This video is about current and resistance. And so some basic vocabulary. We have conductivity, the ability of a material to conduct electricity, like we talked about last time. Resistivity, again, that's a property of the material. Resistance is a property of the material, and it's based on the geometry of the material as well. Ohm is the unit that we use of resistance. It's a volt per amp. Conductors, insulators, and semiconductors. So here, conductors allow charge to flow. Insulators do not allow the flow of charge. But semiconductors are kind of between conductors and insulators. Sometimes they act like insulators. Sometimes they act like conductors. The thing that depends on is the voltage difference across those things. We're not going to study semiconductors in this course. But that's the basis of all of our technology today, semiconductors. Doping, that's when you add small amounts of impurities to either an insulator or a semiconductor to change the electrical properties of it. And superconductors are materials with no resistance, and this happens with materials typically at very low temperatures, and only certain materials they've found this. Some people are trying to work on room temperature semiconductors. It's one of the things going on in science now. I don't know if they've been successful or not yet, but it's something that people were working on. So some review, we have current density, like we talked about before. So we got the Joe equation, J equals sigma E, and E equals rho J. If we take, rho is the inverse of sigma, sigma's conductivity, rho is resistivity. And then we have Ohm's law, V equals IR. So the current through a device is always directly proportional to the potential difference, and it's inversely proportional to the resistance of that object that it's going through. Again, resistivity is independent of magnitude and direction of the applied electric field. It's a property of the material. Resistance depends on the geometry of the material, like we said. And so, moving on. Non-ohmic devices. You'll need to be able to identify this. A material is non-ohmic, or a device is non-ohmic, if V does not equal IR. So if you were to make a graph of potential current versus potential difference, and you get something that's not a line, then it's non-ohmic. Right? So you can see that other side where it's got the two graphs. The first one is ohmic because it follows V equals IR, right? The slope is 1 over R. And remembering that the slope is 1 over R is important. There's a chance that you'll see questions where you're given a graph or you're given some data, and you have to plot the data and get a line. And knowing what the slope of the line is going to be is important, right? I over V is equal to 1 over R, so 1 over R is the slope. That other graph, this is a non-ohmic device because you can see that the current is constant until the potential difference reaches a certain point, and then the current goes way up. This would be an example of a semiconductor, something like that. So example 1, I'm assuming here that you remember resistors, putting them together in series, putting them together in parallel, how that works. Right, so remember, if you put them together in series, R total is R1 plus R2, etc. And then in parallel, 1 over R total is 1 over R1 plus 1 over R2, etc. And so here, R total will always be less than the smallest resistor. And here, R total will always be more than the greatest resistor. Right? And so then we have this set up here. Notice we've got the graph, current versus potential difference, and we want to know which of the slopes represents which of the resistor arrangements. All right, we know that R1 is less than R2. Right. So I versus V, we got to realize that 1 over R, right? V equals IR. So what we have here is actually 1 over r is I over v. Slope here is rise over run. So we're looking at 1 over r. So that means that this is actually the least resistance, and this one is the most. So the most resistance is when you have these in series, which is going to be letter C. And when you have them in parallel, that's D, right? And then R1 is less, so this is going to be A, and that one's going to be B. Okay. And then the graphs to the right in example 2, the first one, letter A, that's ohmic because V equals IR in that. In B and C, V does not equal IR, so neither of those is an ohmic material or an ohmic device. The microscopic view of Ohm's law, this is for information purposes only, looking at velocity and how the velocity is affected by the current density, the electric field, all that stuff. So you can look at that if you want, but you're not going to need to know it. Power. All right, power is the rate of energy transfer from battery to some other device, and the power takes place with joule heating. Right, so it's energy heating, and remember that power is energy energy divided by time. So joules divided by seconds. It's a watt. So if we know energy that's being used up, divide that by the time. But the way we're going to get that here, you can see in the derivation, V is delta U over delta Q. That's potential difference, right? But then if I take that delta Q and I divide by time, then I end up with current. So V times Q over T is V times I. So VI IV is power. That's how much power is being used. And so then for an individual device, you can look at the potential difference across that device divided by R. Because if P equals IV, well, I is V over R. So you get V squared over R. So for an individual device, you can use V squared over R to find how much power that device is using. And then for the battery, you would use V of the battery divided by the resistance, the equivalent resistance of the whole circuit, and that's the power output of the battery. So let's take a look at example 3. Okay, so I just wrote that down without doing any explaining. So I have power dissipated by component of resistance R is P, and then connected to battery VMF. What is the power dissipated by 3 identical resistors if they're connected in series? So if they're connected in series, P, the original P is V squared over R. So then I've got 3R on the bottom. So the power is divided by 3. Think of it this way. You add resistors in series, you're reducing the amount of current that can flow. Since you're reducing the amount of current, you're reducing the amount of power because power is proportional to current. So less current, less power. And in fact, in this case, 1/3 less. For this, RF, is equal to RI over 3. And so the power is going to be V squared over, and then R divided by 3. It's going to be R, and the 3 goes there. So here I've actually got 3 times the amount of power by putting these in parallel. If I put them in parallel, I provide more avenues for that current to flow. So I'm going to get more current overall, and then more power being used up overall. Okay. Batteries. Okay. Almost any 2 different solid conductors immersed in an active electrolyte solution can function as a battery. So that's why you can make a battery out of a potato, out of a lemon. You've got electrolytes in those things. So you take, copper and zinc, and you stick them in there, and now you've got a potential difference because one has more electrons to give away than the other. The electrolyte solution dissolves the ions, allowing the ions to move in the solution. And the cathode is the positive, the anode is the negative, like cations and anions, right? Cathode, anode. If a battery has no internal resistance, then delta V is that It looks like an E, but it's actually a Xi in Greek, but what it represents is EMF. EMF stands for electromotive force, and it has nothing to do with force, but what we'll often do is we'll use that symbol instead of potential difference or instead of voltage. And that's telling us, in the open circuit, the potential difference of the battery. Okay. With batteries, to get a lot of current but low voltage, what I can do is I can add batteries together in parallel. If I want to get a higher voltage but a smaller current, I can add batteries together in series. So I'm increasing the potential difference across the whole series of batteries. And if you want a lot of current and a lot of voltage, you can put them together, put rows of batteries together in parallel. Okay, household applications, we've got kilowatt hours. A kilowatt is power, and you're multiplying it by a time unit, hours. So kilowatt hours is actually an energy unit. It's how much energy has been used, and that's what shows up on energy bills and that kind of thing. And from chemistry or maybe physics last year, the change in potential energy in terms of heat is mc delta T, and that's the energy, so that's power times time, so that's V squared over R times the amount of time that power is being used, and that'll tell you how much something is heated up. We are not going to do calculations with this, but you should see, you are going to need to know things about heat, like joule heating, that when we have electricity going, some of that power could be lost, and then we say, okay, where did that energy go? Well, it goes into heating up the objects. Okay, so example 4. Of course, the hole here is in a bad place. I think it says a toaster using a nichrome heating element operates at 120 volts. When switched on at 0 degrees Celsius, it carries 1.5 amps. A few seconds later, its current reaches a steady 1.33 amps. If the temperature coefficient of resistivity is 4.5 times 10 to the negative fourth per degree Celsius, what is the final temperature of the heating element? Okay. So here R naught is V naught over I naught. So this is going to be 120 volts over 1.5 amps. So that's going to give me 80 ohms. Okay, I know that's the original resistance of this thing. And then our final is VF over IF. And so this is 120 volts over 4/3 of an amp, right? That's the 1.33 amps later on. And so this now is 90 ohms. Right? This thing has changed resistance by 90 ohms. Okay, so now if you remember, this is the rat equation. Delta R, the change in resistance is R naught alpha delta T. All right, and so now I can find the difference in temperature from this. So this is RF minus RI is, or R naught rather, R naught times alpha TF minus TI. I plug in my numbers here. This could be, RF minus R naught over R naught alpha. Let's plus TI, which is 0. And that equals the final temperature. So if we put our numbers in here, we've got 90 minus 80 over 4.5 times 10 to the negative fourth, again times 80. So this is alpha, and that's R naught. I think what we end up with here is 278 degrees Celsius. So that's the final temperature of this toaster. It's exciting. Okay, example 5. Now the heating element of a coffee maker operates 120 volts, carries a current of 2 amps. Assuming all the heat generated is absorbed by the water, that's a big assumption, how long does it take to heat half a liter of water from room temperature, 20 degrees Celsius? So we are doing, I guess we are doing some calculations here. And so delta U, the change in energy, is mc delta T, and that is equal to I times V times T. Right? And so, let's see, time then is going to be mc delta T over IV, and that's it. So the mass is half a kilogram. We're talking about liquid water, so 4184 joules per kilogram. This thing, kilogram degrees Celsius, and then times 80 degrees Celsius. So that's the change in temperature, right? To go from 20 degrees Celsius to 100 degrees Celsius, that's the delta T. And then the current here is 2 amps and 120 volts. Notice we're not doing the change in current here based on resistance, because we're assuming that this thing is at the same heat, the heating element, but now we're heating up the water. So this is the energy used up by the water for this. And it comes to about 11.6 minutes, right, or 697 seconds, and then convert it that way. And then B, how long would it take if the coffee maker was 90% efficient? Well, here for this we can just take this and divide by 0.9, and we get about 774 seconds, right? Because that means that only about 90% of the energy is going into it, right? So it's like dividing by 0.9 is like saying, like taking this thing and multiplying 0.9 by this power that's going into the heating element. Okay, and I believe, oh, we've got a couple more. Example 6, let's take a look. Again, in this problem, power times time, that's the amount of energy that's used up, is mc delta T. Again, I'm looking now for time, right? So time is going to be mc delta T divided by the power. The mass here is 50 kilograms, and it's still 4184. That's the specific heat for the water. And I'm changing this by 10 degrees Celsius. That's the change in temperature. The power here is given to me in horsepower, but 1 horsepower is 746 watts. So I multiply that, the 746, times 100, so I get 74,600 watts. Sorry, it's still watts there. And that gives me a time of 28 seconds. Okay. So now, semiconductors and superconductors, again, we're not doing calculations with these, but you need to know about them. So semiconductors, you can see the resistivity and the temperature. For a semiconductor, as the temperature goes up, the resistivity actually goes down, which seems strange. But then a superconductor, the resistivity decreases, and then it actually just drops to 0 at a certain point, which is pretty amazing. Okay. So semiconductors have a much higher rho than semiconductors. What does it mean if... so semiconductor, what it means then is that it's at a low temperature, is what that means. If a semiconductor has a higher rho, it means it's at a lower temperature, because that's where that happens. At a low temperature, semiconductors, their rho increases. And then what if the semiconductor's temperature coefficient of resistivity alpha is larger in magnitude than for conductors? That means you get a greater change for the same amount of change in temperature. And what does it mean about semiconductors' temperature of coefficient alpha is negative? That means, if alpha is negative, that means that the higher temperature it is, the smaller the resistivity of that material. Okay, and that's it.